sideways, imagine this. You are floating in the endless void of space. Your spacecraft has failed. The engines are dead. Life support is fading. And directly in front of you, pulling you slowly but inevitably toward it, is the most terrifying object the universe has ever created. A black hole. But here is the thing. You're not falling straight into it. Due to the angle of your spacecraft's trajectory when the engines died, you have sideways momentum. You're drifting toward oblivion, but at an angle. And this single fact, this seemingly minor detail about the direction of your fall, is about to create a completely different experience than anyone who falls straight in would ever have. The question burning in your mind, the question that should be burning in everyone's mind right now is simply this. Does it matter? Does the angle of your approach into a black hole actually change anything about your fate? Does falling sideways mean you experience something different than falling straight? Could sideways entry somehow save your life, even for a few precious extra moments? Or does the overwhelming gravity of a black hole simply crush all directions into meaninglessness, making sideways and straight completely irrelevant concepts? These questions are not just thought experiments, they touch the very fabric of reality itself. They challenge everything we think we know about space, time, gravity, and existence. And I promise you, by the end of this journey, the answers will fundamentally change how you see the universe forever. Before we begin this descent into the cosmic abyss, let me hit you with some facts that will prime your brain for what is coming. A black hole can spin at 99.9% the speed of light. Think about that. An object potentially millions of times more massive than our sun, rotating so fast that space-time itself gets twisted into a cosmic tornado around it. Near a black hole, time moves differently. If your feet are closer to the black hole than your head, time passes slower for your feet. In extreme cases, your feet could experience seconds while your head experiences years. You could literally watch your own feet aging slower than your face. Some black holes are so monumentally, incomprehensibly large that you could cross the point of no return, the event horizon, without even feeling anything different. You would pass the boundary between the escapable universe and eternal imprisonment without a single alarm bell ringing in your body. And here is the one that matters most for our journey today. The mathematics, the cold hard equations that govern reality, tell us that falling into a black hole sideways creates completely different physics than falling straight in. Your trajectory, your angle, your sideways momentum, these things fundamentally alter what you experience, how long you survive, and possibly, just possibly, where you end up. If you have ever wondered what happens at the extreme edges of physics, if you have ever stayed awake at night contemplating the strangest objects in existence, if you have ever felt that deep cosmic curiosity that drives humanity to ask the impossible questions, then you're exactly where you need to be right now. What we're about to explore together is a journey that fewer than a fraction of a percent of humans have ever truly understood. This is the story of falling into a black hole sideways, and I need you to focus completely, because every detail matters. Let us start by understanding the monster we're dealing with. A black hole is not actually a hole at all. This is one of the most persistent misconceptions that plagues our understanding of these objects. When you hear the word hole, you probably imagine an empty space, a gap, an absence of something. But a black hole is the exact opposite. It is not an absence, it is a presence. An overwhelming, reality-warping presence of mass compressed into an almost impossibly small space. A black hole is an object. It has mass. It has properties. It exists in space-time as a thing, not as a nothing. Another misconception I need to destroy before we go further is the idea that black holes suck things in like cosmic vacuum cleaners. They do not. A black hole pulls things toward it through gravity, exactly like every other massive object in the universe. If our sun suddenly became a black hole of the same mass, Earth would not be sucked in. We would continue orbiting exactly as we do now, because the gravitational pull at our distance would be identical. The only difference is that the sun's mass would now be compressed into a tiny sphere instead of spread across its current enormous volume. What makes black holes special is not that they pull harder than anything else of similar mass. What makes them special is that you can get so close to all that mass. With a normal star, yes, you cannot get too close because you would hit the star's surface. But with a black hole, there is no surface to stop you. You can fall deeper and deeper into the gravitational well, getting closer and closer to all that mass until the gravity becomes so strong that not even light can escape. That boundary where gravity becomes so intense that light itself cannot break free is what we call the event horizon. And it is the first major landmark on our journey. Black holes have only 3 properties that matter in physics. Just 3 things completely define any black hole in the universe: mass, spin, and electrical charge. Mass determines how heavy the black hole is, how much stuff has been compressed into it. Spin determines how fast it is rotating, and charge determines how much electrical charge the black hole carries. In practice, charge is almost always negligible, because black holes tend to neutralize any significant charge quickly by attracting opposite charges from the surrounding space. So for our journey, we care about mass and spin, and here is where things get fascinating for our sideways fall. The spin of a black hole creates a completely different space-time geometry than a non-spinning black hole. A non-spinning black hole is described by what physicists call the Schwarzschild solution, named after Carl Schwarzschild, who first solved Einstein's equations for this case in 1916. These black holes are spherically symmetric, meaning they look the same from every direction. Falling straight or sideways into a Schwarzschild black hole still matters, but the effects are somewhat simpler to understand. But most real black holes in the universe spin. They spin because the matter that formed them was already rotating, and when that matter collapsed, it spun faster and faster, like an ice skater pulling in their arms. These rotating black holes are described by the Kerr solution, found by Roy Kerr in 1963. And Kerr black holes are where sideways falling becomes truly extraordinary. The rotation of a Kerr black hole does something remarkable to space-time. It drags space-time itself around with it. This effect, called frame dragging, means that near a rotating black hole, space itself is rotating. Even if you try to stand perfectly still, you cannot. Space is flowing around the black hole like water around a drain, and you're carried along whether you like it or not. This frame dragging creates a region called the Ergosphere, a zone outside the event horizon where the dragging effect is so strong that nothing, not even light, can remain stationary relative to distant observers. The ergosphere is shaped like a flattened sphere, bulging at the equator of the black hole's rotation, and this ergosphere is going to be absolutely critical for understanding what happens when you fall sideways versus straight. Remember these terms: event horizon, the point of no return; ergosphere, the region of space dragging outside the event horizon; frame dragging, the rotation of space-time itself. These concepts are the keys to understanding your sideways fate. Now let us talk about the anatomy of a black hole in more detail, because your journey will take you through distinct regions, each with its own bizarre properties. At the center of every black hole lies something called the singularity. For a non-rotating black hole, this singularity is a point, an actual mathematical point of zero size and infinite density. All the mass of the black hole is concentrated at this dimensionless point. Every law of physics as we know it breaks down at this singularity. Our equations give us infinities and absurdities. We simply do not know what actually happens there because our physics is incomplete. But here is something wild for our sideways journey. For a rotating black hole, the singularity is not a point. It is a ring. A one-dimensional ring of infinite density lying in the equatorial plane of the black hole's rotation. This ring singularity has an interior, a space inside the ring. And this creates possibilities for sideways trajectories that simply do not exist for straight falls. Could you somehow pass through the ring? Could you miss it entirely? We will explore these mind-bending possibilities as we descend. Moving outward from the singularity, we encounter the inner horizon, sometimes called the Cauchy horizon, which only exists in rotating black holes. This is a second event horizon inside the main one. What happens at this inner horizon is deeply mysterious. Some theories suggest the physical conditions there are so extreme that it acts as a barrier where our physics completely fails. Others suggest it might be a gateway to other regions of space-time. No one knows for certain, and this uncertainty makes your sideways journey even more intriguing. Further out, we reach the main event horizon, the famous boundary of no return. For a non-rotating black hole, this is a perfect sphere. For a rotating black hole, it is still roughly spherical, but slightly flattened at the poles due to the rotation. The event horizon is not a physical surface. You would not feel it, touch it, or sense it passing through. It is a mathematical boundary defined by the paths that light can take. Inside the horizon, All paths lead to the singularity. Outside, escape is possible. At the horizon itself, light attempting to escape stays frozen, hovering forever. Beyond the event horizon, we have the Ergosphere I mentioned earlier, existing only around rotating black holes. Then further out we find the photon sphere, a region where gravity is so strong that light can orbit the black hole. At the photon sphere, if you aimed a flashlight perfectly sideways, the light would curve all the way around the black hole and hit you in the back of the head. You could theoretically see the back of your own head. This is also where we find what is called the innermost stable circular orbit, or a CO. This is the closest distance at which an object can orbit the black hole in a stable manner. Inside the ISCO, orbits decay. You will spiral inward no matter what. Outside the ISCO, stable orbits are possible. For a rotating black hole, here is the critical fact for your sideways journey. The location of the ISCO depends on whether you're orbiting in the same direction as the black hole's rotation, called prograde, or against it, called retrograde. Prograde orbits can be stable much closer to the black hole than retrograde orbits. This means the direction of your sideways motion relative to the black hole's spin fundamentally changes when you pass the point of no stable orbit. Sideways direction matters. It matters enormously. Let us now understand how gravity itself behaves near a black hole, because this will determine everything about your experience. Einstein taught us that gravity is not a force pulling on objects. Gravity is the curvature of space-time caused by mass. Objects in free fall are simply following the straightest possible paths through curved space-time. Paths called geodesics. Near a black hole, space-time is curved so extremely that these geodesic paths bend dramatically inward. You have probably seen the analogy of a heavy ball sitting on a stretched rubber sheet, creating a dip that causes smaller balls to roll toward it. This analogy is useful but incomplete, because it only shows curvature of space, not space-time. The full picture includes time curvature as well, and this time curvature is what creates the most mind-bending effects. Near a black hole, time runs slower. This is called gravitational time dilation. If you had a clock on your feet and a clock on your head while near a black hole, the clock closer to the black hole, on your feet, would tick slower than the clock on your head. If you could somehow hover just above the event horizon and then return to a space station far away, you might find that years or centuries had passed there while only hours passed for you. This is not science fiction. This is tested, verified physics. So GPS satellites have to account for gravitational time dilation, because the slightly weaker gravity in orbit makes their clocks tick faster than clocks on Earth's surface. Near a black hole, this effect becomes extreme beyond comprehension. The other crucial effect is tidal forces. Because gravity gets stronger the closer you are to the source, and because your body has physical extent, different parts of your body experience different gravitational pulls. Your feet, being closer to the black hole, are pulled more strongly than your head. This creates a stretching force along your body. Simultaneously, because the gravitational field lines converge toward the center, there is a compressing force perpendicular to the stretching. You're being stretched vertically and compressed horizontally. This process is colloquially called spaghettification, and it is exactly as horrifying as it sounds. For a stellar mass black hole, perhaps 10 times the mass of our Sun, the tidal forces become lethal well before you reach the event horizon. You would be ripped apart, stretched into a long, thin stream of particles spiraling into the black hole. But for a supermassive black hole, millions or billions of times the Sun's mass, the event horizon is so far from the singularity that the tidal forces there are relatively gentle. You could cross the event horizon of a supermassive black hole intact, not noticing the crossing at all, and only be spaghettified later as you fell deeper toward the singularity. The size of the black hole determines where you die. This is critical to remember for our journey. Now here is where your sideways motion starts to matter for tidal forces. The tidal stretching is always along the radial direction, toward and away from the black hole. The compression is perpendicular to that. If you are falling straight in radial, the stretching is along your direction of motion. But if you are falling sideways, you have velocity perpendicular to the radial direction. This creates additional stress patterns. You're not just stretched and compressed, you're also twisted, sheared, rotated. The sideways component of your motion interacts with the tidal field in complex ways. Your death, when it comes, will be shaped by your trajectory. Now we need to address a fundamental problem. What does sideways even mean near a black hole? On Earth, Directions are clear. Up is away from the ground, down is toward the ground. Sideways is perpendicular to the up-down direction. Simple, but near a black hole, space-time itself is curved. The notion of direction becomes complicated. Imagine trying to define up and down on a sphere. There is no absolute up. Up depends on where you're standing. Near a black hole, it is even worse. Space is not just curved like the surface of a sphere, it is curved in four-dimensional space-time, twisted by the black hole's mass and rotation. So when I say falling sideways, I need to be more precise. What I mean is falling with significant angular momentum relative to the black hole, as opposed to falling radially with your velocity vector pointing directly at the singularity. A purely radial fall means all your velocity is directed toward the center of the black hole. Your angular momentum is zero. A sideways fall means you have tangential velocity perpendicular to the radial direction. You have angular momentum. You're not aiming straight at the target. You are coming in at an angle. Think of it like throwing a ball. If you throw a ball straight down a well, that is a radial fall. If you throw it at an angle so it spirals around the walls of the well before going down, that is a sideways fall. Near a black hole, your angular momentum, your sideways motion, is not just a curiosity. It is a conserved quantity. Physics demands that angular momentum be conserved, and this conservation law persists, even in the extreme environment near a black hole. Your sideways momentum cannot just disappear. It must be accounted for in your trajectory. This conservation has profound implications. For a rotating black hole, the direction of your angular momentum relative to the black hole's spin creates two fundamentally different scenarios. If your angular momentum is in the same direction as the black hole's spin, meaning you're orbiting the same way the black hole rotates, this is called prograde motion. If your angular momentum opposes the black hole's spin, meaning you're orbiting against its rotation, this is called retrograde motion. Prograde and retrograde trajectories into the same black hole produce dramatically different experiences, different survival times, different visual experiences, different death patterns, different interactions with the ergosphere. The same black hole, approached from the same distance but with opposite sideways directions, gives you two completely different cosmic journeys. This is why your sideways fall matters so much. This is why the angle of your descent is not just a trivial detail, but a fundamental determinant of your fate. Let me introduce one more critical concept before we begin the actual journey: the impact parameter. When astronomers and physicists analyze trajectories near black holes, they characterize the incoming path by something called the impact parameter. This is essentially a measure of how far off-center your trajectory is aimed. If you were flying directly at the center of the black hole, your impact parameter would be zero. If you were going to miss the black hole entirely without gravity bending your path, your impact parameter would be large. There is a critical impact parameter below which you will inevitably fall into the black hole, and above which you can still escape, assuming you have enough velocity. For a given velocity, if your impact parameter is smaller than the critical value, no amount of angular momentum will save you. You will spiral in. If your impact parameter is larger than critical, your angular momentum can keep you in orbit or even allow escape. For our journey, your impact parameter is below the critical threshold. You are going in. But how much below matters? A small impact parameter means you are almost radial, almost a straight fall. A large impact parameter close to the critical value means maximum sideways motion, maximum angular momentum, and the longest, most complex journey into the abyss. Your spacecraft's failure left you with significant sideways momentum. You have angular momentum. You are not falling straight. And this fact is about to take you on a ride that few humans have ever truly contemplated. Let us set the scene for your journey. Your spacecraft has suffered catastrophic engine failure at approximately 1 million kilometers from the event horizon of a rotating black hole. This black hole has a mass of approximately 10 solar masses, making it a stellar mass black hole, the remnant of a massive star that died in a supernova explosion. The black hole is spinning rapidly at about 90% of its maximum possible spin rate. This spin creates a powerful ergosphere and significant frame dragging effects. At the moment of engine failure, your spacecraft had significant tangential velocity. You were attempting a slingshot maneuver, using the black hole's gravity to boost your speed and redirect your trajectory. But now, without engines, that maneuver has become a death sentence. You're trapped on a decaying orbit that will eventually spiral into the event horizon. Your trajectory is prograde, meaning your orbital motion is in the same direction as the black hole's rotation. This will give you the longest possible journey, as prograde orbits can get closer to the black hole before becoming unstable. You have a small window of time before the inevitable, and every second of that window will bring new revelations about the nature of reality. From 1 million kilometers out, the black hole is a dark circle against the stars, but it is not just dark. It is actively bending and distorting the light from everything behind it. Stars that should be behind the black hole hidden from your view are visible. Their light is being bent around the black hole by its immense gravity, creating a phenomenon called gravitational lensing. You see multiple images of the same stars, arranged in an arc around the black hole's shadow. This is called an Einstein ring, and the sight is breathtaking. The universe is literally warped around this object. As you watch, the patterns of light shift because you are moving. Your sideways velocity means your perspective is constantly changing. Stars seem to flow around the black hole like water around a drain. Some stars flicker in and out of visibility as your changing angle brings them into and out of the gravitational lens. A straight fall would show a symmetric view, the Einstein ring centered on your forward direction. But your sideways motion creates asymmetry. The ring is distorted, brighter on one side than the other due to relativistic effects. Light from the direction you are heading toward is blue-shifted, compressed to higher energies. Light from the direction you're leaving is red-shifted, stretched to lower energies. This asymmetry, this visible proof that your trajectory is skewed, is the first tangible effect of your sideways fall. Back on the research station you launched from, your colleagues are watching your signal, but already time dilation is affecting communications. Your radio transmissions are arriving at the station slightly slower than they should. Not dramatically yet, but measurably. Each second that passes for you takes slightly more than a second on the station. As you fall deeper, this effect will compound. A message you send near the event horizon might take years to reach them from their perspective. Though for you only moments have passed since transmission, your sideways motion affects this too. Because you are orbiting as well as falling, your velocity relative to the station oscillates. Sometimes you're moving toward them, sometimes away. This adds Doppler shifts on top of the gravitational effects, creating a complex shifting signal that encodes your spiral trajectory. If they have sensitive enough equipment, they can reconstruct your path from the variations in your signal. They are watching you fall sideways, written in the language of light itself. As you draw closer, the tidal forces begin to make themselves known. At first, it is subtle. You feel slightly taller than usual. Your spine feels gently stretched. The difference in gravity between your head and feet, though still small, is starting to affect your body. You're still hundreds of thousands of kilometers from the event horizon, but the stretching has begun. If this were a straight radial fall, the stretching would be purely along the radial direction, head to toe if you were oriented toward the black hole, but your sideways motion complicates things. As you orbit, your orientation relative to the radial direction changes. The stretching direction shifts. Your body experiences a twisting sensation, a rotation of the tidal stress pattern. It is as if invisible hands are not just pulling you lengthwise, but slowly rotating the direction of the pull. This is the first physical sensation that distinguishes your sideways fall from a straight one. The rotating tidal field synchronized to your orbital motion. You're now close enough that the ergosphere is looming ahead. For a black hole of 10 solar masses spinning at 90% maximum, the ergosphere extends significantly beyond the event horizon at the equator. You're approaching in the equatorial plane, where the ergosphere is thickest. As you enter the ergosphere, something remarkable happens. Even though you are still outside the event horizon, you feel the rotation of space itself. The frame-dragging effect is so powerful here that remaining stationary relative to distant stars is impossible. Space is rotating faster than light speed relative to the external universe. If you tried to hold position here with rockets, you would need infinite thrust. The universe itself is flowing around the black hole, and you are caught in that flow. Because your trajectory is prograde, the same direction as the black hole's spin, you are going with the flow. Yes, space is carrying you around the black hole in the same direction you are already moving. This actually helps you. Your effective orbital velocity relative to the black hole is lower than it would be for a retrograde approach. You're swimming with the current, not against it. If you had been on a retrograde trajectory fighting against the rotation of space, everything would be more extreme. The frame dragging would act against your motion. your effective orbital velocity would be much higher. You would spiral inward faster. The stresses on your body would be greater. The ergosphere would feel like wading through cosmic molasses, while the current pushes you backward. Same black hole, same starting point, but a completely different experience just because of the direction of your sideways motion. Inside the ergosphere, something astonishing is theoretically possible, something called the Penrose Process. If an object enters the ergosphere and splits into two pieces, with one piece falling into the black hole on a carefully chosen retrograde trajectory, and the other escaping outward, the escaping piece can carry away more energy than the original object brought in. The extra energy comes from the black hole's rotation. The escaping piece steals rotational energy from the black hole. This is one of the few known ways to extract energy from a black hole, and it only works in the ergosphere of a rotating black hole. For you, this means something tantalizing. You're still outside the event horizon. Escape is still theoretically possible. If you had a functioning rocket and enough fuel, you could use your prograde motion and the frame dragging to slingshot yourself out of the ergosphere. You could escape, but your engines are dead. The theoretical possibility of the Penrose process mocks you. You have the physics on your side if only you had the technology. Instead, you continue to spiral inward, the ergosphere's frame dragging carrying you relentlessly toward the event horizon. The visual experience inside the ergosphere is unlike anything you have ever seen. Because space itself is rotating, the stars above you seem to streak across your view. The entire universe appears to spin around the black hole at tremendous speed. But this is not just apparent motion from your orbit. This is actual rotation of your local space relative to the distant cosmos. The black hole's silhouette is no longer the simple dark circle you saw from far away. The event horizon's shape is distorted by your proximity and velocity. The photon sphere, where light can orbit, creates a bright ring around the shadow. Inside this ring, you see the event horizon itself, a slightly ablate dark shape due to the black hole's spin. Multiple images and light paths create a complex pattern. Behind you, the stars you've passed are still visible, their light bent around the black hole to reach your eyes. The universe has folded itself into a strange funhouse mirror, and you are at the center. You are approaching the innermost stable circular orbit, the ISCO. For a non-rotating black hole, the ISCO is at 3 times the Schwarzschild radius, where the Schwarzschild radius is a measure of the black hole's size based on its mass. For a 10 solar mass black hole, the Schwarzschild radius is about 30 kilometers. The ISCO would be at about 90 kilometers. But this black hole is rotating, spinning at 90% of maximum. For a prograde orbit, the ISCO is much closer. At 90% spin, the prograde ISCO is at roughly 1.3 times the horizon radius. You can orbit stably much closer to the black hole than you could if it were not spinning or if you were going the wrong way. This is a gift from the cosmos, giving you more time, more experience, more journey before the final inevitable plunge. For a retrograde orbit at the same black hole, the ISCO would be at roughly 4 times the horizon radius. A retrograde faller would have crossed into unstable territory much earlier. They would already be in inevitable plunge while you are still spiraling in the stable zone. The direction of your sideways motion has given you a longer life, but now you cross the prograde ISCO. Below this point, there are no stable orbits. Your spiral is no longer a gradual decay. It becomes an inexorable plunge. Your angular momentum is still conserved, but it can no longer keep you in orbit. You're still falling sideways, but the sideways motion can no longer save you from falling inward. From here, you execute what physicists call a zoom-whirl orbit. You zoom inward, spiral around the black hole in a whirl, zoom out slightly, whirl again, each cycle bringing you closer to the horizon. These zoom-whirl orbits are a signature of the strong gravity regime. They do not exist in ordinary Newtonian gravity. They are a direct consequence of Einstein's general relativity, and you are living them. Each whirl takes you around the black hole. The visual display during these whirls is indescribable. The universe rotates around you, the stars blur and stretch, the black hole's shadow sweeps past your field of view repeatedly. Time dilation intensifies with each inward zoom. Communication with the distant station becomes increasingly difficult. Minutes for you are becoming hours for them. Your messages are stretched into long, slow drawls. Their replies, if they're still sending them, are compressed into brief chirps of noise. The tidal forces are now becoming serious. Your body is stretched by several centimeters. Your spine aches. Your vision is affected by the pressure changes in your skull. The difference in gravity between your extremities is no longer subtle. The twisting effect from your sideways motion adds a rotational component to the stress. Your organs are being gently wrung, not just stretched. This is where the size of the black hole matters enormously. For a stellar mass black hole like this one, the tidal forces are lethal before you reach the event horizon. A supermassive black hole would be much more merciful, allowing you to cross the horizon intact. But you do not have a supermassive black hole. You have a stellar mass monster, and it is tearing you apart slowly with its tidal hands. Still, your sideways motion is doing something interesting. Because you are spiraling, the direction of maximum tidal stretching rotates around your body. This distributes the stress more evenly than a pure radial fall would. You're being killed, yes, but more gently than if you fell straight in. The twisting action gives each part of your body a break as the stretch direction moves on to the next part. It is small comfort, but it is real. Your sideways fall is giving you a few more moments of coherent experience. The event horizon is now close. Through your strained vision, you can see it ahead. A dark surface that is not really a surface. The photon sphere's ring of light marks its edge. The gravitational lensing is so extreme now that you see the entire universe compressed into a narrow band around the black hole's shadow. Everything that exists out there, all the stars and galaxies, all the light of the cosmos is squeezed into a ring around your darkness, and you're about to cross into that darkness forever. There is a debate among physicists about what happens exactly at the event horizon. The classical picture from general relativity says you should feel nothing special at the crossing. It is just a mathematical boundary. The laws of physics do not change. Your local experience should be continuous. You would not know you had crossed except by calculation. But quantum mechanics complicates things. There is something called the firewall paradox, which suggests that quantum effects might create a wall of high-energy particles at the event horizon, incinerating anything that crosses. This paradox arises from conflicts between general relativity and quantum mechanics, and it remains unresolved. We do not know for certain whether the firewall exists. For your journey, we will assume the classical picture holds. You cross the horizon without dramatic fanfare. The tidal forces continue building, but there is no sudden wall of fire. The moment of crossing is subtle. Your trajectory carries you through the mathematical boundary between escape and imprisonment, and you do not feel the moment. What you do notice is what happens to your communication. The instant you cross the horizon, any signal you send will never reach the outside. Light itself is trapped with you. Your colleagues at the station will see your image frozen at the horizon, red shifted into oblivion over time. For them, you never quite cross. You fade into darkness, becoming a ghost image that dims exponentially but never fully disappears. For you, the crossing is instantaneous and unremarkable. The universe of outside has become fundamentally inaccessible. You're in the interior of the black hole now. Inside the event horizon, something remarkable happens to the nature of space and time. Outside the horizon, you have freedom to move in any spatial direction, but you can only move forward in time. Inside the horizon, this changes. The radial direction, toward and away from the singularity, becomes time-like. This means you can no more move away from the singularity than you could move backward in time outside the horizon. The singularity is not a place in space that you are falling toward. It is a moment in time that you are falling toward. It is your future. Every path, no matter which direction you try to move, leads eventually to the singularity. You cannot avoid it any more than you can avoid tomorrow. And this is a difficult concept to grasp intuitively because our everyday experience gives us no preparation for it. But mathematically, the transformation is precise. Inside the horizon, what was a spatial coordinate becomes temporal. Your future is the singularity. Period. However, and this is crucial for your sideways fall, this does not mean you have no control over your path inside the horizon. You can still move in the angular directions. Your angular momentum is still conserved. You can still spiral. You're not falling radially even inside the horizon. You are spiraling toward your future, your path through the interior determined by the sideways motion you carried in with you. For a rotating black hole, this creates fascinating possibilities. The interior of a Kerr black hole is not a simple one-way path to a point singularity. There is structure inside. There is the inner horizon, the ring singularity, and potentially regions beyond that we do not fully understand. Your sideways trajectory will take you on a different path through this interior landscape than a radial faller would experience. The tidal forces are now extreme. Your body is losing structural integrity. Bones are cracking. Tissues are tearing. The stretching has exceeded what human biology can withstand. But you are still conscious, still experiencing. The twisting continues, your organs rotating as the tidal direction cycles with your spiral. You're being wrung out like a wet towel, twisted as you stretch. This corkscrew spaghettification is the signature death of a sideways faller. A straight faller would simply stretch, lengthening into a thin stream aligned with the radial direction. You're stretching and twisting, your material forming a helical stream, a spiral of matter following your spiral trajectory. Particles that were once part of your body are separated, stretched along the flow, but also twisted around each other in a pattern that reflects your angular momentum. Even in death, your sideways motion leaves its mark. You're approaching the inner horizon now, the Cauchy horizon of the rotating black hole. This is a region of intense interest to physicists, because the mathematics become very strange here. General relativity predicts that an observer crossing the inner horizon would see the entire future history of the external universe flash before their eyes, infinitely blue-shifted and compressed into a single instant. All the light that will ever fall into the black hole arrives at the inner horizon simultaneously from the perspective of a crosser. This creates what is called a mass inflation singularity. The energy density at the inner horizon becomes infinite. The inner horizon itself becomes singular. This suggests that nothing can actually cross the inner horizon intact. The physical conditions are too extreme. Your sideways trajectory will take you to the inner horizon at a specific point, determined by your angular momentum. A radial faller would hit the inner horizon at a different point with different conditions. Does the angle matter for what happens at the inner horizon? Probably not. The singularity there is likely lethal regardless of trajectory, but we do not know for certain. Our physics breaks down. This is the frontier of human knowledge. If somehow the inner horizon does not destroy you, if our understanding is incomplete and the singularity there is not as absolute as we think, then your sideways journey would continue toward the ring singularity itself. For a Kerr black hole, the singularity is a ring in the equatorial plane. A radial faller heading straight for the center would hit this ring directly. But a sideways faller with angular momentum would spiral around it. Could you miss the ring? Could you pass through the center of the ring, into the region that mathematical analysis suggests exists there? The mathematics of the Kerr solution implies that the region inside the ring singularity has bizarre properties. It contains closed time-like curves, paths through space-time that loop back on themselves in time. It might connect to other regions of space-time entirely, other universes perhaps. Whether any of this physical reality or just mathematical artifact remains unknown. But your sideways trajectory, with its conserved angular momentum, would take you on a different approach to the ring than a radial faller. If anyone could thread the needle, it would be someone coming in at an angle, spiraling rather than plunging straight. This is pure speculation, of course. We have no experimental data about the interior of black holes. We have only mathematics and guesswork. But your sideways fall gives you a trajectory that, at least mathematically, has more options than a straight fall. Let us now step back from your specific journey and compare the full experience of falling straight versus falling sideways. The approach phase differs dramatically. A straight faller heads directly toward the black hole, seeing the symmetric Einstein ring grow larger as they approach. A sideways faller spirals inward, seeing an asymmetric shifting lightscape as their angular motion carries them around the black hole. The duration of approach differs as well. A straight faller takes the shortest path, reaching the horizon in minimal time. A sideways faller takes a longer spiraling path, especially for prograde motion around a rotating black hole. More time to experience, more time to observe, more time to transmit data before the final plunge. The interaction with the ergosphere differs fundamentally. A straight faller passes quickly through the ergosphere, experiencing frame dragging briefly. A sideways faller spends extended time in the ergosphere, feeling the rotation of space dragging them along, or fighting against their motion depending on their direction. Prograde sideways motion goes with the flow, retrograde fights it. The experience of crossing the innermost stable circular orbit differs. A straight faller does not have a stable orbit to lose. They were never in orbit. A sideways faller experiences the transition from decaying orbit to inevitable plunge, the crossing of a stability threshold that marks the beginning of the end. The visual experience at the horizon differs. A straight faller sees the symmetric view, the universe compressed into a ring centered on their forward direction. A sideways faller sees an asymmetric view, the ring shifted and distorted by their tangential motion, relativistic effects creating brightness differences around the ring. Spaghettification differs qualitatively. A straight faller is stretched radially, elongated along their direction of motion into a long, thin stream. A sideways faller is stretched and twisted, their material forming a helical pattern, a corkscrew of particles spiraling into the singularity. The survival time differs significantly. A straight faller takes the minimum time path to the singularity. A sideways faller takes a longer spiraling path, gaining additional seconds or fractions of seconds of conscious experience. For a stellar mass black hole, these are tiny differences. For a supermassive black hole, the difference could be substantial, minutes or hours of additional survival for maximum angular momentum. The approach to the singularity differs for rotating black holes. A straight faller heads for the ring singularity directly. A sideways faller spirals toward it, potentially approaching from a different angle or with different possibilities for threading the ring. The bottom line is that falling sideways is objectively different from falling straight. The physics changes, the experience changes, the death changes. In the universe of black hole falls, trajectory matters. Now let me take you deeper into some of the most mind-bending implications of black hole physics, because your sideways fall connects to some of the biggest mysteries in physics. First, the information paradox. When you fall into a black hole, what happens to the information that describes you? In quantum mechanics, information cannot be destroyed. The complete quantum state of a system must be preserved forever, at least in principle recoverable. But a black hole seems to destroy everything that falls in. The singularity is the end of all world lines. Nothing that falls in ever comes out, at least not until the black hole evaporates. And when a black hole evaporates through Hawking radiation, the radiation appears to be thermal, random, carrying no information about what fell in. This is a contradiction. Either quantum mechanics is wrong about information preservation, or general relativity is wrong about what happens inside black holes. Or there is something subtle happening that preserves information in a way we do not understand. Your sideways trajectory contains information. The angle of your fall, your angular momentum, your rotational direction relative to the black hole's spin. Is this information preserved somehow? The holographic principle suggests that information about what falls into a black hole might be encoded on the event horizon itself, preserved in a two-dimensional form even as the three-dimensional objects are destroyed in the interior. If so, your sideways trajectory might be written on the horizon in some subtle way, your angular momentum becoming a pattern in the horizon's quantum structure. We do not know. This is one of the deepest unsolved problems in physics, but your sideways fall is part of the puzzle. Second, wormholes and other universes. The mathematical solutions for rotating black holes contain more than just our universe. When physicists extend the Kerr solution as far as the mathematics allows, they find that the interior of a rotating black hole connects to other regions of space-time. These regions might be other parts of our universe, incredibly distant from us. They might be entirely separate universes. They might be mathematical artifacts with no physical reality. The connection through the black hole interior is what physicists call an Einstein-Rosen bridge, or wormhole. Could you, with your sideways trajectory, navigate through a rotating black hole to emerge somewhere else? Almost certainly not, unfortunately. Even if the wormhole connections are physically real, the conditions at the inner horizon and singularity are almost certainly lethal. The theoretical traversability of wormholes requires exotic matter with negative energy density that probably does not exist. Your angular momentum might give you a different approach to the interior structure, but it probably cannot save you from its hostility. Still, the fact that your trajectory matters, that the angle of your fall affects your path through the interior, leaves open the tiniest crack of cosmic possibility. If we are wrong about anything, if any of our assumptions are incomplete, then sideways might just be the key. Third, quantum gravity. Our current physics is incomplete. General relativity describes gravity beautifully at large scales, but gives us infinities and singularities at small scales, places where the theory breaks down. Quantum mechanics describes physics at small scales, but has not been successfully combined with gravity. The singularity inside a black hole is exactly where we need a theory of quantum gravity, a unified theory that combines both frameworks. We do not have such a theory yet. String theory is one attempt, loop quantum gravity is another. Both are incomplete and untested, but both suggest that the singularity might not be the infinite density point or ring that classical general relativity predicts. In loop quantum gravity, for example, the singularity is replaced by a quantum bounce. Matter falling in might bounce back and emerge somewhere else, perhaps into another universe. If something like this is true, then your trajectory, your sideways fall, might determine where you bounce to. Your angular momentum might be preserved through the bounce, affecting the nature of what emerges. We are in the realm of speculation here, but the incompleteness of our physics means that surprising things might be true, and your sideways fall, with its conserved angular momentum and distinctive trajectory, might matter in ways our current theories cannot capture. Let me share what we have actually observed about black holes to ground our speculation in reality. For decades, black holes were theoretical predictions that we had never directly observed. We inferred their existence from the effects they had on nearby matter, from X-rays emitted by superheated gas spiraling into them, from the motions of stars orbiting invisible massive companions. But in recent years, we have begun to observe black holes directly. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole, the supermassive black hole at the center of the galaxy Messier 87. The image showed the black hole's shadow, the dark region where light cannot escape, surrounded by a bright ring of emission from the superheated gas in the accretion disk. The asymmetry of the ring, brighter on one side than the other, told us that the gas was moving relativistically, approaching us on one side and receding on the other. The black hole's rotation was imprinted in the light. In 2022, the same collaboration released an image of the black hole at the center of our own Milky Way galaxy, Sagittarius A star. This black hole is smaller and more variable than the one in M87, making it harder to image, but the shadow was there, surrounded by the same telltale ring of emission. Gravitational wave astronomy has given us another window on black holes. Since the first detection in 2015, the LIGO and Virgo collaborations have detected dozens of black hole mergers, events where two black holes spiral into each other and combine. The gravitational waves from these mergers carry detailed information about the masses and spins of the black holes, the angle of their orbit, the final black hole produced. Every merger involves sideways motion. The black holes do not fall straight into each other. They spiral, dancing gravitationally until their final plunge and merger. The gravitational wave signals encode this spiral motion, this sideways trajectory writ large on the fabric of space-time itself. For our specific scenario, a stellar mass black hole of 10 solar masses, we have observed many such objects through their effects on companion stars in binary systems. These black holes are real, they are out there, and matter is constantly falling into them, almost never straight, almost always with angular momentum, almost always sideways. The accretion disks around black holes are made of matter falling sideways. The gas spirals inward, radiating energy as it goes, getting hotter and hotter until it emits X-rays, before finally plunging through the innermost stable circular orbit into the event horizon. This is sideways falling on a cosmic scale, and we observe it happening across the universe. Let me now paint a series of hypothetical scenarios to explore the full range of sideways falling possibilities. Imagine you had a perfect spacecraft capable of incredible thrust, and you entered a black hole's ergosphere on purpose. Could you orbit inside and survive? For a while, perhaps. You could hover in the ergosphere, burning tremendous fuel to fight the frame dragging if you wanted to stay still, or coasting along if you went with the rotation. You could descend slowly, exploring, taking measurements, but eventually you would run out of fuel, or you would cross the event horizon, intentionally or by mistake, and then no amount of thrust could save you. Inside the horizon, you cannot escape even with infinite engine power. The universe does not allow it. But the time you could spend in the ergosphere, the observations you could make, would be invaluable for physics. The frame dragging, the gravitational lensing, the time dilation, all could be measured directly. Imagine you fell into a black hole with a friend, but at different angles. You take a prograde trajectory, your friend takes retrograde. You enter the ergosphere at the same moment. but your experiences immediately diverge. You feel space carrying you along with the black hole's rotation. Your friend feels space fighting their motion, dragging against them. Your time dilation differs. Your visual experiences differ. The tidal stresses come at different times. You might try to communicate, but your signals are affected by the complex space-time geometry. You might lose contact entirely, each of you spiraling toward the singularity on separate paths, never able to reconnect. You would die different deaths at different times by your own clocks, approaching the singularity from different directions, your particles joining the black hole's mass in different patterns. Same starting point, same black hole, but fundamentally different fates based solely on the direction of your sideways motion. Imagine the black hole was electrically charged. This adds another property to the black hole, changing its geometry. Charged black holes have two horizons even without rotation, and with rotation they become even more complex. The interior structure changes. The singularity might be avoidable under some circumstances, with certain trajectories passing through the interior without hitting it. Your sideways motion, combined with any charge you carried, would interact with the black hole's electromagnetic field as well as its gravitational field. The physics becomes richer, more complex, and the trajectory dependence becomes even more significant. Imagine you are not a human-sized object but a quantum particle. At the quantum scale, everything changes. Your position is not definite but described by a probability distribution. You might tunnel through barriers that classically would stop you. You would be affected by Hawking radiation, the quantum process by which black holes slowly evaporate. Near the horizon, your quantum state would interact with the vacuum fluctuations that create Hawking radiation. A straight falling particle and a sideways falling particle might have different quantum interactions, different probabilities of being part of a Hawking radiation pair that escapes. At the quantum scale, your trajectory might determine whether you escape or fall in a way that the classical trajectory does not capture. Let us contemplate the human element of this journey. You're falling into a black hole sideways, and you know you're going to die. This is the ultimate one-way trip. No possibility of return, no possibility of rescue. The physics is absolutely certain. You will reach the singularity, you will be destroyed. But in the time you have, what would you experience mentally? Would there be peace in the certainty, fear, wonder? Time dilation gives your final moments a strange character. From your perspective, you experience a finite time from horizon crossing to spaghettification. For a stellar mass black hole, this is very brief, fractions of a second perhaps. For a supermassive black hole, it could be hours. But from the perspective of the outside universe, you never quite reach the singularity. You fade at the horizon, frozen and redshifting forever. In some sense, your final moment is stretched across cosmic time. Your last thought, if it could be transmitted, would reach the distant universe only after eons. There is something profound in this. Your final experience, brief as it is for you, echoes across all future time for external observers. You become eternal in your ending. The great physicists who contemplated these questions were moved by them beyond mere mathematics. Kip Thorne, who worked out much of the physics of black hole interiors and time dilation, was inspired to collaborate on the movie Interstellar, bringing these concepts to a mass audience. Stephen Hawking, who discovered Hawking radiation and sparked the information paradox, devoted his life to understanding the deepest mysteries of black holes and the universe. Roy Kerr, who solved Einstein's equations for rotating black holes in 1963, gave us the mathematical foundation on which all our understanding of sideways falling rests. These were humans grappling with the infinite, using mathematics as their language, and they found beauty in the terror, meaning in the mystery. Your sideways fall is part of a cosmic pattern that plays out across the universe constantly. Matter rarely falls straight into anything. Angular momentum is everywhere. Planets orbit stars. Stars orbit galactic centers. Galaxies orbit in clusters. Everywhere you look, things are moving sideways. The universe prefers circular motion, sideways motion, to simple straight falls. This is because angular momentum is conserved, and the vast majority of matter has some. When clouds of gas collapse to form stars, the angular momentum flattens them into disks. When matter falls toward black holes, it almost always has angular momentum, forming accretion disks rather than falling straight in. The sideways fall you're experiencing is not exotic. It is normal. It is how the universe works. Straight falls are the rare exception, requiring special circumstances where angular momentum has been removed. Your death is the cosmic default. In contemplating your journey, we touch on questions that go beyond physics into philosophy and even spirituality. What does it mean to fall into a black hole? What does it mean to be destroyed in a singularity? Is there any sense in which you continue to exist after your particles are torn apart and absorbed into the black hole's mass? From a materialist perspective, you cease to exist when your brain is destroyed by tidal forces. The pattern that was you is ended. From an information theoretic perspective, you might continue to exist as information encoded in the black hole, eventually released in Hawking radiation billions of years hence. From various spiritual perspectives, your consciousness might continue beyond physical destruction in ways that physics cannot address. These questions have no scientific answers, but they are worth contemplating as you fall. The sideways motion that distinguishes your journey from others, that gives you extra moments to think, that twists your death into a unique pattern, might just give you the frame of mind to face the infinite with something like equanimity. As your journey approaches its end, as the tidal forces cross the threshold from painful to lethal, as your consciousness begins to fade from a body that can no longer maintain coherent thought, there is one final observation to make. The black hole will be slightly changed by your fall. Your mass, tiny as it is compared to 10 solar masses, will add to the black hole's mass. Your angular momentum, your sideways momentum will add to the black hole's spin. The pattern of your spiral will imprint itself in the geometry of the event horizon, ripples that propagate and eventually settle into a new equilibrium. You will have kicked the black hole ever so slightly. If your trajectory was prograde, you will have spun it up a tiny bit. If retrograde, slowed it down a tiny bit. Your sideways fall leaves a permanent mark on the cosmos, not much of one, unmeasurably small, but real. Your existence mattered to the universe, even to this monster that destroys everything it touches. You gave it a gift of angular momentum that it will carry forever, or at least until it evaporates in the unimaginably distant future. In the end, this is what remains of your sideways journey. A tiny change to the spin of a black hole. A microscopic alteration to the geometry of space-time itself. It is not nothing. It is something. And perhaps that is enough. The singularity approaches. Your trajectory, determined by that initial sideways momentum when your engines died, has carried you on a unique path through the most extreme environment in the universe. You have experienced things no straight-falling object could experience. You have spiraled where others plunged. You have twisted where others merely stretched. You have seen the universe from an angle that only a sideways faller could achieve. And now, at the end, your matter joins the matter of countless other objects that have fallen into this black hole over its millions of years of existence. Your particles will never escape, at least not in any recognizable form. Perhaps, in unimaginably distant time, your information will leak out in the subtle correlations of Hawking radiation. Perhaps your angular momentum will be felt in the spin of a quantum gravity bounce in a universe we cannot imagine. Perhaps there is nothing beyond the singularity but an end to all story. We do not know. Physics does not know. But your sideways fall has been completed now, and it was different from a straight fall in every way that physics can describe. You mattered. Your angle mattered. In the universe of black hole death, direction makes a difference. Sideways is not the same as straight. For those who will never fall into a black hole, who will live their lives far from any event horizon, what lessons does this journey offer? Perhaps this, that even in the face of absolute fate, absolute certainty of destruction, the path you take matters. The choices you make, even choices that do not affect your ultimate destination, affect your journey. How you fall matters even when falling is inevitable. This is true at the cosmic scale of black holes, and it is true at the human scale of our mortal lives. We are all falling toward an ending. None of us escapes. But the angle of our fall, the sideways motion we carry, the trajectory we trace through space and time, these things shape our experience. They determine what we see, what we feel, what we leave behind. They make our journey uniquely ours. So fall well, fall with intention, fall sideways if you can, because the extra moments, the different view, the unique pattern you leave in the fabric of reality, these things matter. They are all that matter. The cosmos is vast and strange. full of objects and phenomena that challenge our intuition and exceed our imagination. Black holes stand among the strangest of all, regions where space-time is twisted beyond recognition, where time and space exchange roles, where the very concepts of past and future lose their familiar meaning. And yet, even in this most extreme environment, physics continues to function. Conservation laws continue to hold. Angular momentum is preserved. Trajectories can be calculated. Your sideways fall is describable, predictable, distinguishable from a straight fall by cold mathematics. The universe plays by rules, even at its most violent edges. This is perhaps the most remarkable thing of all. That existence is lawful, that we can understand it, at least in part. That a species of apes on a small planet orbiting an ordinary star in an unremarkable galaxy can deduce the behavior of falling objects near singularities millions of light years away. The human capacity for understanding is itself a cosmic phenomenon, perhaps the cosmos becoming aware of itself, trying to understand its own nature through minds that it has somehow produced. Your sideways journey into a black hole is a thought experiment conducted by the universe upon itself, using the minds of creatures who will never experience such a fall, but who can imagine it with astonishing accuracy. We are the universe, falling sideways into its own deepest mystery, wondering what we will find. The journey we have taken together in this exploration has covered enormous ground. We began with a simple question. Does falling sideways into a black hole make any difference? We have found that the answer is yes, unequivocally yes. The direction of your fall, your angular momentum, the angle of your approach, these things fundamentally alter your experience, your survival time, your death, and your ultimate fate. Sideways falling interacts differently with the ergosphere of a rotating black hole. Sideways falling gives you more time outside the horizon and more time inside before reaching the singularity. Sideways falling creates tidal stress patterns that twist as well as stretch. Sideways falling takes you on a spiral trajectory through the black hole interior that differs from a radial plunge. Sideways falling, in a rotating black hole, brings you to a ring singularity rather than a point singularity, sees us with potentially different implications for what lies beyond. These differences are not mere curiosities. They are fundamental to the physics of black holes. They are measured in the gravitational waves from black hole mergers. They are seen in the accretion disks that surround active black holes. They are encoded in the spin of every black hole in the universe, a record of the angular momentum of everything that has ever fallen in. The universe keeps track. The universe knows whether you fell straight or sideways, and that knowledge is inscribed in the fabric of space-time itself. We have also touched on the deepest mysteries of physics, questions that remain unanswered despite decades of effort by the greatest minds. What happens at the singularity? What resolves the information paradox? What does quantum gravity look like? These questions are connected to your sideways fall because your trajectory is information, your angular momentum is a quantum number, and your ultimate fate depends on physics we do not fully understand. In pursuing these questions, we push at the boundaries of human knowledge, extending our understanding inch by inch into the unknown. Every answer generates new questions. Every mystery solved reveals deeper mysteries beneath. This is the nature of science, the endless quest that defines our species. And your sideways fall, imaginary as it is part of that quest. So what happens if you fall into a black hole sideways? You spiral instead of plunging. You experience the frame dragging of the ergosphere. You see the universe from a unique asymmetric perspective. You survive longer than a straight faller. You die twisted as well as stretched. You approach the singularity on a helical path, and you leave a tiny but permanent mark on the black hole itself, your angular momentum adding to its spin for eternity. Your sideways fall is not the same as a straight fall. It never was. The angle matters. The direction matters. In the extreme physics of black hole interiors, every detail matters. This is the universe we live in, precise, mathematical, beautiful, terrifying, and absolutely indifferent to human notions of what should and should not matter. The cosmos does not care whether you fall straight or sideways, but the cosmos does keep track, and if you ever find yourself falling toward a black hole, remember this. Go sideways, buy yourself a few more moments, see something no one falling straight could ever see. A twist instead of merely stretching. Make your death as unique as your life. because in the end, the journey is all there is. The destination is the same for everyone, but the path, the angle, the sideways momentum, these are yours to choose. The universe awaits your fall. Make it count. And so we come to rest at the end of this journey, having travelled from the first curious question to the final mysterious singularity. We have explored the anatomy of black holes, the nature of space-time curvature, the mathematics of rotating systems, the physics of tidal destruction, the philosophy of information and existence. We have imagined ourselves falling, spiraling, experiencing, and ultimately being destroyed by the most extreme objects the cosmos contains. Through it all, one truth has emerged with clarity. The angle matters. Sideways is different from straight. Your trajectory shapes your destiny even when your destination is certain. This is a lesson for black holes and for life. How you travel matters as much as where you arrive. The cosmos, in its infinite complexity, has woven meaning into motion, significance into direction, consequence into the angle of a fall. If you take nothing else from this journey, take this. The way you approach the darkness determines what you see on the way. The momentum you carry determines the path you trace. The direction you choose changes everything about the journey, even when it cannot change the end. Look up at the night sky tonight. Somewhere out there, a star is dying, collapsing in on itself, forming a new black hole. Somewhere out there, gas is spiraling into an existing black hole, radiating X-rays as it falls. Somewhere out there, two black holes are dancing their final dance, spiraling toward merger, sending gravitational waves rippling across the cosmos. All of this is happening right now, at this very moment, as you read these words. The universe is falling into itself, matter spiraling into oblivion, space-time twisting into knots that will never untangle, and you, a conscious being made of the same atoms that spiral into those black holes, a thinking creature arising from the same cosmos that contains such monsters, you have just spent this time understanding a tiny piece of that vast and terrifying reality. You have asked the question, you have received an answer, and the answer is yes. Falling sideways makes a difference. In the universe of black holes, direction matters. Even at the end of all things, how you fall is who you are. End.